The problem of spinning was one of the earliest troubles to be investigated by aerodynamicists of the Royal Aircraft Establishment, and quite a lot of research went into finding the reason why certain machines were more inclined to this condition than others, discovering ways and means to lessen the tendency, and the easiest way to recover from it. These early experiments in 1925 were carried out in a balloon shed. The models were released and their behavior recorded by cine cameras. The models had a free fall of about 100 feet. This method had its limitations, and a vertical wind tunnel was considered. This miniature tunnel proved that the idea was practical, and a larger tunnel was constructed in 1931. It was 12 feet in diameter, 30 feet in length, and had an airspeed of 30 feet per second. In this, the aircraft could be studied and recorded for longer periods. The cine records provided the means of assessing the rate of rotation and angle of spin. With this Gamecock undergoing spinning tests, it was found that by raising the tailplane, a speedier recovery from a spin was effected. During the spinning experiment, the controls could be changed at a predetermined instant by means of a dashpot. These recovery experiments show the dashpot in action. The controls are reversed when the flag is released. Recovery from a flat spin is a difficult and slow business. With the raised tailplane, the spin is steeper and the recovery rate faster, as can be seen. An early aeroplane called the Hill Pterodactyl. This machine, having dispensed with the customary tailplane, was of a revolutionary nature, and we shall see it again. An aeroplane of the 1950s. The tunnel was in use till 1957. A new departure in spinning experiments is being carried out with a 5th scale Javelin aircraft. The model is suspended from a balloon at 3,000 feet, rotated and then released. In this case, cameras fitted with 36 and 50-inch lenses were necessary to obtain a picture large enough to be seen and measured accurately. These give the camera operator less than 1.5 degrees field of view and make the tracking of this fast-moving aircraft very difficult. Again, the controls are automatically changed at a predetermined time to effect recovery from the spin. When recovery is complete, a parachute is released which prevents damage on landing. These pictures, taken from the balloon with a normal speed camera, give some idea of the true speed of the model and the consequent difficulty of following it and obtaining a reasonably steady picture with the ground cameras. You've seen a model of this machine in the spinning tunnel, the Hill tailless aeroplane. The controls are being tested prior to a test flight. The flight took place in April 1926, before the days of self-starters and runways. Aircraft had no smooth tarmac to help them with their takeoff run, and with their low-powered engines no doubt found the going heavy before being airborne. As compared with the biplanes of those early days, this aeroplane presented an entirely new aspect, and there is no doubt it showed the shape of things to come. Another departure from normal was the fitting of air brakes. With these, it was possible to prevent stalling at low speeds and also considerably reduce the landing run. An interesting experiment was carried out in 1925 when attempts were made by squadron leader Hager Haig to hook on to a DH-53 light aeroplane to the airship R-33. We see the aircraft attempting to connect with a crossbar suspended below the airship, the idea being perhaps that the aeroplane could be used for defense or some other purposes. A second camera, looking vertically downwards, gives you a different view of the same attempts. It was not an easy job, but the trials were finally successful and proved that it was possible to launch an aircraft and attach it again in flight. The scheme was never developed further, as airships are no longer with us, but a seed was sown, and a parent aircraft is not an unknown quantity these days. With the urge to go further and faster, the problem of increasing the range of aircraft was an early task allotted to the RAE. The first successful experiments were made in 1924 and carried out by two Bristol fighters using 60 feet of 3/4-inch hose. This more ambitious attempt with two Vickers Virginias took place 6 years afterwards. Here contact has been established, but they've decided not to button up. In these experiments, the cine camera played an essential part in the trailing angles of differently weighted pipelines and their general behavior at varying speeds and lengths. These two Virginias eventually succeeded in passing 50 gallons of fuel through an 1.25-inch hose, but not without a certain amount of risk. The old machines were apt to wallow, and a loose flapping pipe could be very trying for the observer in the back, with the risk too of damaging the tailplane. It is evident now that things are not too comfortable. Anything might happen. Well, that's better. They seem to have complete control again. With this successful contact, refuelling is taking place. A snatch would now prematurely end operations, and some skill is needed to keep the correct formation. Fortunately, despite the hazards, there were no accidents, and refuelling in the air was proved to be a practical proposition. With this fact established, some other schemes were investigated, and the ideas passed on to industry, where they have since been developed. With the refuelling finished, the machines break apart and go their separate ways. The observation machine from which the cine records were taken is coming into land. The aerodrome in those early days was very small compared with its present size. There were no tarmac runways, no control towers, and a small hut served to clock aircraft in and out. With the increasing speed of aircraft, another problem, wing flutter, made itself apparent. This full-scale wing of a Gamecock is undergoing wind tunnel tests, and from these pictures taken at 100 per second, it was possible to measure the amount and period of flutter. In recording airflow over wing sections, wool tufts are sometimes used. The stalling characteristics can be easily seen and recorded with cine cameras. Visual observation is difficult and unsatisfactory, but the camera produces a permanent record quickly, and so saves wind tunnel running time and costs. The film can be analysed at leisure. With the full-scale air test, the camera is again essential. This aircraft is a Falcon, doing stalling tests. The wool tufts show plainly on which part of the wing surface stalling commences. Airflow can also be readily seen by means of white oil spread upon the wing surface. This is an ideal method for recording photographically, and where wool tufts show the airflow above the wing surface, the white oil tells a more intimate story of the air in direct contact with the wing. The flow pattern is easily seen and recorded. Another trouble that developed as aircraft improved their performance and were able to fly higher, longer, and in all sorts of weather, was ice accretion. Several methods were investigated to free control surfaces of ice. This wing section in a wind tunnel under icing conditions is being photographed at 1/6 the normal speed, the action thereby being speeded up 6 times. With a subject such as this, slow motion photography is called for and helps considerably in assessing the wash of the floats with the varying seas and speeds. This machine is the Gloucester 1, an early aspirant for the Schneider Trophy. This is a Seagull, a product of the early 20s, the first flying boat of the RAF. The Atalanta, an early attempt to produce a larger aircraft. Archival, the Valencia. The hull is graduated so that the wash can be assessed. The one and only mobile high-speed cine camera was kept very busy in these early days. A jump to 1939. In this year, the Lyric was undergoing a testing period. To more fully investigate the troubles of flying boats, the RAE constructed a tank in 1930. It was 660 feet long and with a carriage speed of 40 feet per second. This model, undergoing porpoising tests, is suspended from a carriage that records the stresses imposed during its journey down the tank. A cine camera is mounted on the carriage, and from the records obtained, its behavior under the varying conditions applied to it can be recorded and studied. Full-scale trials were also recorded of the early ditching experiments. With the growing use of aircraft at sea, many schemes to keep aircraft afloat after emergency ditchings were tried. In this instance, a Nimrod is being deliberately ditched to test the efficiency of airbags that inflated automatically on contact with the sea. This slow-motion record gives a false impression of the actual speed, which was obviously higher than intended. From the camera records, speed and angle of entry could be determined. It was a relief to see the pilot get clear. With experiments endangering human lives, it is imperative that all possible information is obtained, and the cine camera record is invaluable. Models were also used to study ditching characteristics. From pictures such as these, the best angle and speed of entry can be estimated. This is not a good ditching. During the early 20s, radio-controlled pilotless aircraft were being developed in the RAE. The Larynx was designed to carry a 250-pound bomb and had an operating range of 300 miles, the first guided missile. From this, the Queen Bee emerged as a gunnery target aircraft. Some 500 were made and used by the Army and Navy. This trial took place at Invergordon in 1934. Cinematography played an essential part in all this development, frequently producing the answer as to how and why things went wrong, and they sometimes did. Despite the slow speed and low altitude, these target aircraft proved difficult to hit. Success sometimes rewarded the effort. When the Navy adopted aircraft again in the early 20s, landing and takeoff techniques were studied with the aid of cine cameras. This DH-9 landing on HMS Argus was taken at normal speed. Judged by present-day landing speeds, it may appear as slow motion. With this takeoff experiment of a Fairey 3F on a free trolley, the deck has been calibrated to help in the assessment of the record. These calibrations, together with a 50-cycle timing mark on the edge of the film, provide an accurate basis for analysis. Later, with the development of catapults, the camera played its part in recording the speed and clearances of the superstructures. In this particular instance, a dummy aircraft is being catapulted in a crosswind to find the limitations under crosswind conditions. The lengthening of the time scale by taking slow motion pictures makes the viewing and assessing easier. Now a live launch. The aircraft is a Fairy 3D. This time a seagull. From this picture the acceleration and launching speed can be ascertained. One of the first landings on HMS Courageous in 1931, using a hook and arrestor wires, which had now become necessary with the increased landing speed of aircraft. To check these speeds and angles of approach, cinematography proved to be the only practical method. To obtain better records, a camera boom was built out from the ship's side. With the camera normal to the flight path, speeds and angles were more accurately measured. The camera is operated remotely. The operator, with his back to the scene, views through a monocular the aircraft on a mirror fitted beneath the camera. Operating a sea fire landing. The pictures are taken at normal speed. This slow motion record of a helldiver landing tells the whole story. The arrestor hook is for some reason missing all the arrestor wires. There is evidence of the brakes being applied. The crash barrier deals with the emergency. The beginning of a new era. The first jet lands on HMS Ocean in 1945. The pilot was Lieutenant Commander E.M. Brown, RN, the aircraft a Vampire. It was something of an occasion, apparently. These pictures of a Seahawk are taken for interest and record purposes only, but at the same time other high-speed cameras are disposed along the deck, recording landing speeds and rate of descent. Similarly, takeoffs are photographed. Catapult speed and acceleration can be measured accurately and the stresses on the aircraft calculated. If things go wrong, the cine records go a long way in establishing why. As with everything else, things will go wrong. Here is an early misfortune on HMS Argus, our first aircraft carrier. This is more serious and a near miss for the cine camera. A swordfish in trouble. If they will come in too fast, what else can be expected? The pilot seems none the worse. Another looking for trouble. This type of approach cannot be recommended. Unfortunately, in this crash, a piece of the prop struck the camera operator, who was seriously injured. For aircraft that miss the arrestor wires, crash barriers have been designed to prevent overrun into the sea. And this mosquito is being used to test the efficiency of the barrier. The aircraft comes off second best. Wooden aeroplanes would seem to be unsuitable for carrier work. A later trial showing the development of a nylon barrier with a more modern type of aircraft. The machine is finally arrested with a minimum of damage. An advance in deck landing technique has been achieved by the angle deck. This air view of HMS Centaur shows parked aircraft on the starboard side with still a clear run left for aircraft landing on. The ship's captain, Captain H.B. Sears, RN, made the first landing on this deck with an Avenger, followed by Seahawk landings. A further improvement has been obtained by the use of the mirror deck landing aid. These lights are reflected from mirrors which produce a pitch-stabilized light beam set at the aircraft's optimum glide path and guide the pilot straight onto the deck. This has proved very successful and greatly relieved the work of the landing signal officer, normally known as the batsman. Barring accidents, the safety factor of aircraft is high. Wings, fuselages, tailplanes, undercarriages, and all essential structures undergo rigorous tests to ascertain their safety factor and useful life. Here, a Lancaster wing is undergoing a fatigue test. The wing is being vibrated at 5 periods per second, and according to the amount of this treatment it can stand, so can be determined its useful life in flying hours. The wing has fractured. With tests such as these, camera installations play an essential part. It will be impossible for any number of observers to note or agree where failures commence or occur. With this wing under continuous and increasing load, the formation of the buckling that occurs as the load increases can be easily detected by lighting the wing in a suitable manner. Perhaps the biggest job in structure fatigue tests was carried out at the RAE when investigating the Comet disasters in 1953. The complete aircraft was submerged in a water tank, gust loads applied to the wings, and cabin pressures adjusted to flight conditions. With the increasing speed of aircraft, the gravitational effects on pilots became a subject for considerable study. The CIDIC camera again played its part in recording the effects of G and the resulting blackout. In this early test, the aircraft is spinning, and the G is being recorded on the second instrument from the bottom in the left-hand corner. At the moment of blackout, the subject operates a light that is seen in the center of his harness. His resistance to G, or threshold, can now be established. On this rocket trolley, a dummy man is being used to test the strength of the harness. Now the human guinea pig. The trolley and track have been calibrated so that deceleration can be measured from the pictures. It is all very essential that the human frame and harnesses are capable of withstanding the stresses imposed upon them in this age of ever-increasing speed. The well-being of this volunteer, who is about to be snatched into the air, depends upon the soundness and strength of the harness he is wearing. It may appear that it is hanging on a thread. The airman clinging to this aeroplane is about to drop off to test the Irvine parachute, which was being adopted by the RAF in 1924. These initial trials are made at Henlow during that year, and it was the first time, at least in this country, that the slow-motion cine camera was airborne for the cause of aeronautical research. The camera, a bulky one, was mounted on the gun ring and fully exposed to the slipstream. It was difficult to operate and made control of the aircraft rather tricky. With modern aircraft, the high speeds made climbing out impossible. One had to be ejected. Here are early wind tunnel tests with models. And now the full scale. The removal of the cockpit hood is not always possible before being ejected. With the slow motion record, a picture-by-picture analysis will show clearances or damage that might occur during the ejection. Extensive seat ejection trials were carried out from a Canberra aircraft. Special tracking mountings were designed to enable high-speed cine cameras fitted with lenses up to 80 inches focal length to be operated at high angles of elevation. This ejection seems to be unsuccessful. Again, a picture-by-picture analysis will bring to light when, where and why things started going wrong. Seat ejection trials at a height of 40,000 feet have been successfully recorded from the ground with cameras fitted with 36 and 50-inch lenses. These pictures were taken at a lower altitude. Here is another attempt. This time things seem to be working satisfactorily. The timing of the various functions can be checked and any abnormalities noted. Now a low-level ejection. The timing and operation of the various components must work to plan if one is to make a safe landing at low altitude. By lengthening the relative time scale by using slow-motion cinematography, one is able to check any malfunctioning of the apparatus. If things do not go as planned, visual observation is of little use with things moving so quickly. During the Second World War, the dropping of men, armament and supplies of all sorts became an urgent necessity. A lot of research went into designing parachutes for dropping the smallest containers to those needed for such things as trucks or air-sea rescue boats. For these heavy loads, multiple parachutes are used. Should things go wrong, lines become entangled or the canopies damaged in any way, the cine record becomes invaluable. Extensive trials were carried out to determine their performance, the speed and height from which they could be dropped and their loading capacity. At Ringway, the wartime parachute training establishment, cine cameras were in constant use recording the practice jumping of paratroops, and at one time every jump was photographed with 16mm cameras fitted to the aircraft. By this means it was possible to account for the extremely rare fatality and to take the necessary steps to prevent recurrence. The films also played an important part in enabling the men to study landing techniques and in this way rectify their faults and lessen landing casualties. The risk of fire should an aircraft crash or sustain damage through hostile action has always been a danger, and to combat this, considerable work has been done by the RAE. These early firefighting suits were designed in 1935. They were the first of their kind and no doubt pointed the way for further development by other concerns. The major effort went into the prevention of fires either by self-sealing fuel tanks, the automatic spraying of methyl bromide, or the introduction of nitrogen to displace the explosive air present in the tanks, in this way to minimize the effect of incendiary bullets. This tank is obviously unprotected. In this picture, yet another explosion suppression device is employed, and it is obvious that the incendiary bullet has had no disastrous effect. The unprotected tank, identical in all respects, but without the suppressor device, tells a different story. This, no doubt, would have meant the loss of an aircraft. Research into ballistics is another activity of the establishment, and again the cine camera plays an important part. This is an early experiment to increase the dropping, height and range of torpedoes. From carefully aligned cameras on surveyed points, the true trajectory can be calculated. The wings are released by the operation of a trailing weight or impact with the water. Another early bomb fitted with a parachute and designed for a special job. The slow-down cine record shows clearly that the parachute is not functioning correctly. This time the fault has been remedied and all seems to be well. The ballistics of bombs are studied from release to impact. Here is a slowed-down picture taken from an accompanying aircraft. The bomb is then tracked down by manually operated ground cameras, fitted with long focus lenses and with specially designed mountings that will enable the heavy high-speed cameras to be elevated at a high angle and manipulated at a fast tracking rate. Some skill is needed to follow bombs dropping with their high velocities, and as commercial tripods are not obtainable for this sort of work, tripods and mountings have been designed that will permit the camera to be mounted and operated through the centers of gravity, and to help tracking through large angles of elevation or azimuth, to have the sighting arrangements as near as possible to the optical axis of the lens. These pictures of inert bombs dropped from high altitude onto a concrete target were obtained by remotely controlled fixed cameras. The pictures, taken at 240 per second, show the motion down 10 times, and from these records terminal velocities were measured. In addition, higher speed cameras were employed to measure the deceleration on impact. You can see a pressure wave travelling outwards from the bomb. These pictures were taken at 3,000 per second. In all, there were 8 high-speed cameras, all remotely controlled in the target area, and no casualties. With rocket development, the cine camera again played an important role. Here, an early static test. Now the swordfish. And the hurricane. These are post-war trials with the Vampire. Any misbehavior of the rockets at release or during the trajectory can be easily seen. To rely on human observation will be totally inadequate. In addition, from records such as these, the speed and striking velocities can be determined. This model rocket aircraft, undergoing release tests in the wind tunnel, was made to investigate transonic and supersonic flight. The full-scale test took place off the Scilly Isles in 1948. Where it was released from a Mosquito aircraft and reached a speed of 930 miles per hour in level flight. Our first venture into the supersonic region. To study the airflow in wind tunnels of bodies likely to be subjected to subsonic or supersonic speeds, Schlieren photography is used to make visible the airflow around the model. In this picture, the tunnel speed is being increased, and one can see the change that is apparent as the speed goes through the sonic to the supersonic region. Considerable skill is needed in tracking the full-scale rockets. The slow-motion camera makes it appear easier than it is. In this particular instance, a pressure wave becomes visible for a short period. This phenomena only appears under certain atmospheric conditions and is a very infrequent occurrence. With such costly experiments as these, it is essential to have complete film coverage. From the high-speed and theodolite recording cameras, the speed, trajectory and the general behavior throughout the entire flight can be assessed. In conclusion, it is considered that wherever science is leading us on this planet or others, the cine camera will still continue to play its all-important role in aeronautical research and development.